Okay, so let's go ahead and get started with your Truss solution here. Before I get into the actual solution, I'm going to go ahead and just put down three general rules for us to get started with. And the first one is in terms of what order we'll solve for. So the first one is I'm going to solve for static determinacy. Okay, and that will, just a little formula if you remember that we start off with, to determine whether we can even mathematically move forward and solve the truss. We'll go through each steps individually. The second step is we're going to solve for external forces first. And then the last step that we will do is we will solve for internal forces. Okay, so moving on, we're going to jump right into step number one of the steps that we just listed out here, static determinacy. So we're going to move in, and that's problem number one. If you remember, we have a formula, 2J is equal to M plus R, whereas J stands for the number of joints in our truss, M stands for the number of members, and R stands for the number of reaction forces. So it's great that we've got that formula, but we don't yet have our reactions, the R's labeled yet, and that's actually step two. So let's get that done. We notice that we've got two different supports here. One a pin and another a roller, and hopefully you know by now that a pin has two reaction forces associated with it, and we're going to label that as the reaction force at point A in the X, and likewise we're going to label another reaction force here at point A in the Y direction. Okay. On the other side we see that we have a roller support, and I'm just going to quickly draw in a small arrow here, and I'm going to call that the reaction force at point D in the Y. So at this point, we've got our three labeled reaction forces. Question number two is done, and then we've got a good formula to work from. So let's go ahead and substitute our values in. 2J, the number of joints, 1, 2, 3, 4. So that'll be 2 times 4. On the other side of our equation, we have the number of members, 1, 2, 3, 4, 5, plus the number of reaction forces, 1, 2, 3. A little bit of math. 8 equals 8, and that balances and that checks, and we can move on with our equation. Number 2 is already done. So back to our original list here, static determinacy. We're done with that as well. We can move on to solving for external forces, which we will do in problems 3, 4, and 5. So our starting point here is that, reading the question, find the reaction force at D of Y by summing the moments around point A. And what's that saying is that we're locking the truss here, and we have a force. We're going to look at the forces that are acting in the Y, okay, and moving this thing in relation to point A that we're fixed. So we see that we have a force of 1,750 pounds here right below point C, and then we have a reaction force of D of Y and a reaction force of A of Y. And those are the things that we'll all solve for first in our external forces. So let's get reaction force at D of Y first. We're going to do that by summing the moments around point A. So we're going to just start with an equation that says the sum of the moments at point A should equal 0. If you'll remember from earlier in the year, a moment is a force in a distance, and we have a force here in a distance, we have a distance here, but no force, so that's the force we're going to solve for. So we're going to set up an equation that mirrors that. So we're going to write an equation that says the force of C, or the moment of C, I apologize, plus the moment of D should equal 0. So we'll substitute in our forces and distances for those moments here. So the moment of C is comprised of a 1,750 pound force, and we're going to actually label that as a negative. Why are we labeling it as a negative? Because it's going down. And we see the distance there of times 9 feet, and we're going to add that to the moment of D. Well, what do we have at D? We don't know the reaction force RDY, so that's unknown, but we do have a distance of 14 feet, so we substitute that in, and that all should come to equal 0. So at this point, we're going to get out the calculator and just do a little bit of math and say that a negative 1,750 times 9 should equal negative 15750. Again, we're going to say we're going to add that to our equation. Let's just step through the algebra here. And I'm going to say plus 14 RDY. I apologize about that, but 14 RDY. Okay, and this is still in pounds. So we have negative 1575 plus RDY equals 0. What are we going to do? We're going to add 15,750 to each side of our equation. And the next form of our equation will look like 14 RDY is equal to 15,750. Okay? At that point, we're just going to simply isolate and try and get RDY by itself, so it makes sense that we divide by 14. And we're going to wind up with RDY being equal to, let's see what we get here as we plug it in, 15750 divided by 14 equals 1125. 1125 pounds, and that is our reaction force of R dy. So number 3 is done. Okay, moving on to number 4. The question says find the reaction force at A of y by summing the forces in the y direction. So we're not considered with moments anymore. We're just going to add those forces together, knowing that they should all balance at 0 to prove that we're in static equilibrium. Okay, so let's do that. We're going to set up just a simple statement here that says the sum of the forces in the y direction should equal 0. And then we're going to substitute in the 3 forces that we see in the y. And what do we see? We see a reaction force at A of y. We see a force at point C that's acting downward in the y. And if you want, you can label that as a negative 1750 if that'll help you. And then we have the reaction force at R dy, which we just found to be 1125 pounds. So let's add, we need to have a formula that reflects that. So we're going to take the reaction force at A of y, we're going to add that to the force of C, and then we're going to add that to the reaction force at R dy, and that should all equal 0. So let's substitute in some values here. We still don't know Ray, but we do know the force of C, and it's actually a negative 1,750 pounds. Okay, plus the last force that we had for R dy, we solved that already. That's the reaction force at R dy, and that's 1,125 pounds. Okay, and that's going to be equal to 0. So we can do a little bit of algebra here and just take the negative 1750 and add it to the 1125. So let's do that. Negative 1750 plus 1125. Oops, I'm sorry, that came out as a minus. So negative 1750 plus 1125 should equal a negative 625. So we're left with an equation that looks like that Ray minus is 625 pounds because we got a negative value is equal to 0. So we add 625 to each side of the equation and we wind up with Ray is equal to 625 pounds. Okay, and there we are. So we've got Ray now, 625 pounds. Okay, the last thing we have to do, and that's 2 of our external forces. Now we know the reaction force at R dy, we know the reaction force at Ray, we know this other force that was given to us, the initial force, and the last thing that we have to solve for is the reaction force at A in the x, because we do have a reaction force in that A of x and we do need to know what it is. So the first thing was, again, as always, we're going to set up an equation that says the sum of the forces in the x direction should equal 0. And well, do we have any forces actually in the direction of 0? Is there an initial force anywhere on a truss acting in the x? And there isn't. So we're going to just say the reaction force at A of x is equal to 0. Because there is no initial force, there can't be no reaction force. Okay? So that's it. If we come back to our original list here of solving for static determinacy, solving then for external forces, we're done. That first part of those first 2 steps are done. And we're going to flip over to the other side of our page and use some of this information now to solve for the rest of our internal member forces. We've solved for static determinacy, we've solved for our external member forces, and now we're going to move forward and solve for the last things, our internal forces. So let's flip our page over here, get an idea for what we're looking at. It says, step 7 says solve for the internal forces in members AB and AC. So we're going to actually solve for this force and this force first. Okay? Before we do that, I want you to write down just a couple general rules that I think will help you out. Remember, when we find out the forces in our members, we need to identify whether they're in tension or compression. So we'll start with that, with a little rule that helps us with that. So first, remember, if we find a value to be positive, it is in tension. So again, we can write the word tension and put a positive next to it just as a reminder. And then if we find a member to have a negative answer, it's going to be a member that's in compression. So a number here that gives us a positive value is a member that's in compression, and a numerical answer here that it comes up as a negative tells us that that member is in compression. Okay, tension and compression. The other thing too that I think is helpful to write down is that when we are solving for and using for solving for things in the y direction, we're going to use the sine function. Y equals the sine function. And when we solve in the x direction, forces in this direction, we're going to use the cosine function. Okay. And you'll see that come up clearly here in just a minute. So let's move through and solve these last couple steps here. Okay, so solve for the internal member forces of A and B. So what do we need to do? We need to set up an equation that allows us to do that. So we're going to do AB over here. Okay, we'll draw a little bit of a line here to split this page up, and we're going to do AC, the other member here. So AB first, which is this member here. Okay, so the first thing we have to do is again set up an equation that says the sum of the forces at point A in the Y is equal to 0. Okay, so the sum of the forces at this particular point in the Y direction should equal 0. And so what we need to know right away is how many forces are acting in the Y. Well, there's a reaction force in the Y right here that we see, and then also this member has a Y quality to it because it is going up. So we flip back over and we're going to just quickly write an equation. It says the reaction force at A of Y plus the force of the member AB in the Y is equal to 0. Okay, because those are the things that are acting on point A. We found out on the other side of the page that our reaction force at A of Y was 625 pounds, so we're going to substitute that in. 625 pounds. Plus, then we have the force of AB that we need to calculate for. So the force of AB, which is unknown to us at this point, but we can represent that value, again, because we're looking at something in the Y direction with the sine function. And again, we could draw out this triangle individually and use SOHCAHTOA to prove why we're using the sine function, but it comes back to the basic tenets of SOHCAHTOA. So we're going to say force of AB times the sine of the theta angle that we have there. So the force of this member times this theta angle should tell us the value. 39.43 is equal to 0. We're going to just do a little bit of algebra here at this point to isolate so that we can get to that force of AB. So we're going to subtract 625 pounds from each side of our equation. And the next line of our equation should look like the force of AB times the sine of 39.43 is equal to negative 625 pounds. At that point, we're going to just divide by the sine of 39.43. Okay, 39.43. Those will cancel so that we can isolate for the force of AB. And at this point, we're ready to get out the calculator and just do a little bit of math. So we've got negative 625 divided by the sine of 39.43 is equal to a negative 984. And it's actually negative 984.04. I'm going to round up to the nearest whole number. So we'll just call it a negative 984. And we see that it's a negative value. What does that tell me at the top of my chart? Negative is in compression. So we're going to just quickly label that. And what I'm going to do is really quickly flip over to the other side of my page and show the value for that right there. Negative 984, which is the force that we just figured out, AB, into as a member that is in compression. Okay? Moving right along here, we're going to go over and solve for this force of AC. Now we need to know this force. Okay? So, again, we're going to say the sum of the forces at point A in the X should equal 0. Okay? So what forces are acting in the X? Well, we have this reaction force that's acting in the X. This member is definitely acting in the X. And then this member, while it is going up, is also going to the right, so it has an X value. So we're going to write an equation that reflects that. So first we're going to say the reaction force at A of X plus the force of AC, the member AC, which we do not know, and then the force of AB, but it's X quality in the X, which is equal to 0. So let's substitute some values in now. The reaction force at A of X we found on the other page was 0, so we're going to use that value. 0 plus, we don't know the force of AC, that's what actually we're solving for, but we do know some information about the force of AB. So we do have that value. We know that the force of AB was negative 984 pounds. And again, when we earlier said that when we're going to do a X calculation, figure anything that has X value, we're going to use that cosine function. So we're going to go ahead and do that. And we're going to say negative 984 times the cosine of 39.43 is equal to 0. And again, we could prove why we use sine and cosine by just drawing these out and using SOHCAHTOA in its basic form. So at this point, we're ready to do a little bit of math. Now, the next line of our equation will look like the force of AC plus, okay, what's going on in our parentheses here. So we're going to say a negative 984 times the cosine now of 39.43 is equal to a negative 760 pounds. Is equal to 0. So all we have to do at this point is we want to isolate for the force of AC, so we're going to add 760 to each side of our equation. And we're going to find that the force of AC is 760 pounds. And again, it's a positive number, so we're going to label that as tension. Flip back over and I'll put that right in here. Okay, so negative 700, or positive 760 pounds. 760 pounds. And I'm going to say tension. Okay, you can put a T or a C, whatever you want to do, okay, but just so long as it's labeled. So we've got two forces there labeled, plus our reaction forces that we have known down here. Moving right along, we've got to solve again for, and we're done with this side of the truss. We're going to move over to the other members, members BD and members CD. Okay, so again, we'll follow the same format. It's asking the same exact thing, solve for the internal member forces at BD and CD. So let's do BD over here. And we're going to do CD over here. And we're really just going to replicate the process. So I'm going to speed right along here and go through it again. So here we're going to say the sum of the forces at point D in the Y is equal to 0. Again, we're looking at this point and saying what forces are acting in the Y. And just like the other side, we saw a reaction force, and then this member has force. So we write an equation that says the reaction force of RDY plus the force of member BD in the Y should equal 0. On the other page, again, we can move forward and just substitute some values in. On the other side of the page, we found the reaction force at RDY to be 1,125 pounds, plus the force of BD, which is unknown to us, but we can know that, again, we're calculating a Y value, so we're going to use that sine function times that theta angle, and that angle is 52.6 degrees. Times 52.26 is equal to 0. Do a little bit of algebra here, subtract 1,125 from each side of our equation, and we're left with the next line of our equation looking like the force of BD times the sine of 52.26 is equal to a negative 1125. Okay? Again, at this point, we're just going to divide by the sine of 52.26 on each side, so that we can get force of BD by itself, and we're going to grab the calculator at this point. So again, we're going to clear this up. We're going to say a negative 1125 divided by the sine of 52.26 is equal to a negative 1422.6, so I'm going to round that up to a negative 1423. Again, we see that as a negative value, so we're going to say that it's in compression. Okay, and let's go over to the front side of our page and label that. So force BD is negative 1,423, and we're going to, because it's negative, it is in compression. Okay, we've got two last members to solve for, and we're done. So let's move right along here with the force of CD. Again, we're going to say that the sum of the forces at point D in the X is equal to 0. The sum of the forces at point D in the X is equal to 0. Okay, so we first have to ask the question, what forces do we see at point D? Well, the only forces that we see there are this member force and this member force. So we're just going to build an equation that reflects that. We're going to say that the force of CD plus the force of BD in the X now is equal to 0, because again, we're looking at this truss, this vector, and it has both Y and X qualities. So we substituted some values in if we have them. The force of CD is still unknown to us, but we do know the force of BD, which we just figured. The force of BD is a negative 1,423, and we're going to multiply that again. We're doing an X value, an X calculation, so we're going to say the cosine of our angle, 52.26, is equal to 0. We're going to get out the calculator at that point again, and we're going to say a negative 1423 times the cosine of 52.26 should equal a negative 870.9 pounds. So I'm going to just say, I'm going to round that up to 871. That's the next line of our equation after we've done the math in the parentheses. And what do? We simply add 871 to each side of our equation. And we're left with the force of CD is 871 pounds. And again, it's a positive number, so it is in tension. Go over and label that now. The force of CD, we can go back over here and say 871, and we're running out of space, so I'm just going to put the T there. Awesome, we're almost done. We got one last thing to solve for, and that is the force, the internal member forces in BC from point C. So we're asking, what is the force at this member in relation to that? So again, just like we've seen, we should, because we're working in static equilibrium, we should be able to add those values together to come to 0. So again, we'll write an equation, the sum of the forces at point C in the y. Sum of the forces at this point in the y direction. So what do we have? We have two forces that are acting in there, that particular point. We have the force of C itself, the weight, plus the force of the member, BC, should equal 0. This member plus this force should equal 0. We're just going to substitute some values in. We know that the force is negative 1750, the force of C is negative 1750. We do not know the force of BC. We simply add 1750 to each side of our equation, and we are left with the force of BC being a positive 1,750 pounds. We go back in, label this 1750, I'm sorry, skipped one step here, 1,750 pounds, positive, tells me that that member is in tension. Last thing I do is come in, 1,750 pounds, label that with a T, again because we're rolling out of space, and we are all set and done. If you really want, you can come in and place in these forces, 1125, apologize there, and RAY we found to be 625. And we have met all the requirements. We have solved for all static determinacy, we have solved for our external forces first, and then we used some of that information to help us solve for the internal forces. And that's the truss. Hopefully that'll help, and that's all I have.